120 light-years from our planet, a powerful telescope has captured a discovery that could fundamentally reshape humanity's understanding of life in the universe. The James Webb Space Telescope has detected a planet where the surface temperature consistently hovers at 120 degrees Fahrenheit. This astonishing world is enveloped in a dense atmosphere, within which scientists have clearly observed chemical signatures typically associated with living organisms. Experts express 99.7% confidence that this is precisely what they've been searching for, a planet teeming with life and possibly even more hospitable than our home Earth. Prepare yourselves as we begin our captivating narrative. The sensational data arrived one Tuesday morning in December, carefully hidden within massive terabytes of infrared radiation collected by the most advanced cosmic eye ever created by humanity. Niku Madhusudan stared intently at his computer screen at Cambridge University, meticulously examining the wavelengths of light that had traveled 120 light-years to reach Earth. What he saw made his hands tremble involuntarily with excitement. In the spectrum of light that had passed through the dense alien atmosphere, a marker was found that, by all laws of nature, simply shouldn't have been there. Dimethyl sulfide, DMS, a complex compound produced on Earth exclusively by living organisms through their metabolic processes. And it wasn't just a faint hint, but a powerful and distinct signal, so strong that the probability of measurement error was less than 0.003%. The James Webb Space Telescope had accomplished what every scientist on our planet had dreamed of. It provided irrefutable evidence of life beyond our solar system. The planet, designated K2-18b, orbits a red dwarf star in the so-called habitable zone, where liquid water could theoretically exist. However, this world is fundamentally different from anything we've ever seen in our solar system. It is 8.6 times more massive than Earth and surrounded by a hydrogen-rich atmosphere. This creates such a powerful greenhouse effect that vast oceans remain liquid beneath alien skies. The temperature readings were simply astonishing: 120 degrees Fahrenheit, warm enough for life to thrive, yet cool enough to prevent complete evaporation of water. Madhusudan's team spent months studying this amazing world, using the Webb telescope's incredible sensitivity to peer through the planet's dense atmosphere during its transits across its star. Each such transit revealed new and astonishing secrets. First, the presence of water vapor was detected, then methane, and later carbon dioxide. But the detection of dimethyl sulfide was the real turning point. This molecule is so closely linked to biological processes that its discovery in another planet's atmosphere is like finding a bright neon sign loudly proclaiming the existence of life. The magnitude of the discovery struck the scientist like a powerful blow. If confirmed, this finding would forever end humanity's cosmic solitude. We would no longer be alone in the universe. The probability calculations were simply staggering. 99.7% confidence that the signal was real, not random noise or interference. In the world of astronomy, where certainty is extremely rare and discoveries are often refuted, such a level of confidence is unprecedented. However, K2-18b is not just another planet. Its unique characteristics make it potentially more habitable than Earth itself. The hydrogen atmosphere acts like a giant blanket, trapping heat and creating stable conditions across the planet's surface. Unlike Earth's thin nitrogen atmosphere, this dense hydrogen envelope can maintain liquid water over a much wider range of temperatures and pressures. The star K2-18, which the planet orbits, is a red dwarf, smaller and cooler than our Sun, but much more stable. While our Sun will eventually swell into a red giant and destroy all life on Earth, red dwarfs can burn for trillions of years, providing a steady supply of energy for eons. Any life that could have evolved on K2-18b would have had virtually unlimited time to reach levels of complexity surpassing humanity's wildest fantasies. As Madhusudan prepared to share his discoveries with the world, he realized that this particular December morning would forever be remembered as the moment everything changed, the moment humanity learned it was not alone in the universe. But this was just the beginning of a story that would forever alter our understanding of life. the universe, and our place in this vast and mysterious world. Scientists had long believed that to find life, one needed to find an Earth-like planet, a rocky world orbiting a sun-like star at the perfect distance for liquid water. However, K2-18b completely shattered this established notion. This planet proved that life can arise in utterly alien conditions where we would never have thought to look. Perhaps that's where we should be looking for life. Planet K2-18b belongs to the class of so-called super-Earths, celestial bodies larger than our planet but smaller than Neptune. Until recently, astronomers considered these planets uninhabitable, envisioning them as gas giants whose mass was too great to support known forms of life. However, K2-18b has forced the scientific community to reconsider its ideas about what an habitable world might look like. This planet's mass creates gravity almost 3 times greater than Earth's. Thus, a person weighing about 150 pounds on Earth would weigh over 400 pounds on K2-18b. Nevertheless, this immense gravity could be beneficial for the existence of life. The intense gravitational field retains the atmosphere, preventing its dissipation into space, as happened with Mars's atmosphere billions of years ago. K2-18b's atmosphere itself contradicts scientists' previous notions of habitable worlds. Instead of the oxygen and nitrogen we breathe, this planet's atmosphere is dominated by hydrogen and helium. On Earth, hydrogen is a trace gas making up less than 1/millionth of our atmosphere. On K2-18b, hydrogen is the primary component of the atmospheric envelope, creating a completely different environment. This hydrogen atmosphere creates an effect that scientists call a runaway greenhouse effect, but with an inverse sign. Instead of heating the planet, like Venus, hydrogen acts as a perfect insulator, maintaining a stable temperature across the planet's surface. The dense atmosphere redistributes heat so effectively that even the planet's night side, never illuminated by sunlight, remains warm enough for liquid water to exist. The chemical signatures detected by the James Webb Space Telescope paint a picture of a world where life has not only originated, but is thriving. Alongside dimethyl sulfide, indicating the presence of life, the atmosphere contains methane, carbon dioxide, and water vapor, a combination of molecules indicative of active biological processes. On Earth, these gases are produced by all sorts of organisms, from bacteria to complex living beings, creating a planetary metabolism detectable from space. But perhaps most surprising is the absence of ammonia in K2-18b's atmosphere, a molecule that would predominate if the planet were a lifeless gas giant. This is compelling evidence that biological processes are actively removing ammonia from the atmosphere. Life is not just present on this planet, it is actively shaping its atmospheric chemistry. The discovery of K2-18b shows that the universe may be full of life in places we never expected to find it. If life can originate and thrive in the hydrogen-rich atmosphere of a super-Earth, then the number of potentially habitable worlds in our galaxy could be hundreds of times greater than previously thought. Red dwarfs like the star K2-18, which make up 3/4 of all stars in the galaxy, suddenly become priority targets in the search for extraterrestrial life. The implications of this discovery are astounding. Perhaps we are not looking for an Earth twin, but its strange cousin, thriving in conditions so alien that we are only now beginning to understand them. The James Webb Space Telescope is not just the most powerful space observatory in human history. It is a time machine, allowing us to peer deeper into space than any instrument ever created. 1 million miles from Earth at a gravitational equilibrium point called L2, the Webb telescope exists in eternal darkness. Its enormous sunshield blocks heat and light from our star, keeping the instruments colder than the surface of Pluto. The telescope's main mirror is 21 feet in diameter, nearly 3 times larger than the Hubble telescope's mirror. However, it's not just size that defines Webb's revolutionary capabilities. The mirror is made up of 18 hexagonal segments, each coated with a microscopic layer of gold, reflecting infrared light with unprecedented precision. These segments work together to create a mirror so perfectly aligned that it can detect the heat signature of a bumblebee on the moon. Infrared light is invisible to the human eye, but it is key to detecting life on distant planets. As planets pass in front of their stars, a minuscule portion of the starlight filters through their atmosphere before reaching Earth. Different molecules absorb specific wavelengths of infrared light, creating unique fingerprints that the Webb telescope can detect with extraordinary sensitivity. The complexity of detecting these molecular signatures is almost incomprehensible. Imagine trying to spot the light of a firefly hovering next to a bright searchlight from 1,000 miles away. The star K2-18 is billions of times brighter than the planet orbiting it. Nevertheless, the Webb telescope is capable of capturing the faint infrared glow of molecules in the planet's atmosphere with high precision. The Webb telescope has revolutionized astronomy with its high precision. Webb's secret weapon is its coronagraph. Originally designed to block starlight and detect objects hidden in its glare, it employs advanced imaging techniques. These methods subtract the overwhelming brightness of the star, revealing faint infrared signatures of atmospheric molecules. This can be compared to using a sophisticated filter to dampen the roar of a jet engine and hear a faint whisper. To detect dimethyl sulfide on K2-18b, the Webb telescope had to operate at the very limits of its capabilities. The molecule produces such a faint infrared signal that several observations over several months were required to confirm its presence. Each observation captured only a few photons of light that had traveled 120 light-years through the vacuum of space, carrying information about the possibility of life on another world. But Webb's most outstanding achievement, perhaps, is its ability to measure temperature with incredible accuracy. The telescope detected that K2-18b maintains a surface temperature of precisely 48.9 degrees Celsius, 120 degrees. Warm enough to support liquid water, yet cool enough to prevent its complete evaporation. This temperature measurement, accurate to within a few degrees across interstellar distances, represents one of the most precise measurements ever made for an exoplanet's environment. The data processing required to extract these discoveries from raw infrared observations involves some of the most advanced computer algorithms ever developed. Artificial intelligence systems analyze millions of data points, searching for patterns that would be invisible to the human eye. The discovery of life on K2-18b is not only a triumph of engineering, but also a testament to humanity's ability to push the boundaries of what is possible. Webb has fundamentally changed our understanding of the cosmos. We are no longer merely wondering if life exists elsewhere. We are actively observing its signs. 48.9 degrees Celsius. This number seems almost too perfect to be true. It's the temperature of a hot summer day in Death Valley, the warmth of a relaxing hot tub, the feverish heat of a human body fighting an infection. On K2-18b, it's the temperature that makes life possible on another world. Temperature is a key factor when it comes to life. Too cold, and water freezes into ice that cannot support the complex chemical reactions necessary for life. Too hot, and water evaporates, leaving behind a lifeless desert. The range in which liquid water can exist, what scientists call the habitable zone, is surprisingly narrow. Earth is almost precisely in the middle of this zone around our sun, a cosmic accident that has allowed life to thrive for billions of years. But K2-18b's ideal temperature is no accident. It is the result of a delicate balance between the star's energy and the atmosphere's chemical composition, creating conditions more stable than anything found on Earth. The planet orbits its red dwarf star at a distance where it receives almost the same amount of energy per square meter as Earth receives from our sun. This cosmic coincidence means that, despite being 120 light-years away, K2-18b exists in virtually the same thermal environment as our own world. The hydrogen atmosphere plays a crucial role in maintaining this ideal temperature. Unlike Earth's thin nitrogen atmosphere, which allows heat to escape quickly into space, K2-18b's dense hydrogen envelope acts like a planetary blanket. Hydrogen molecules trap infrared radiation, creating a greenhouse effect that keeps the planet warm even on the night side, which never sees sunlight due to the planet's synchronous rotation. This stable temperature creates something unprecedented in our solar system. a world where liquid water can exist everywhere, from the perpetually day side to the perpetually night side. On Earth, temperature variations between day and night, summer and winter, poles and equator create complex weather phenomena and climate zones. On K2 to 18b, the dense atmosphere redistributes heat so effectively that the entire planet maintains a constant life-favorable temperature. The implications for the existence of life are simply astounding. Temperature fluctuations on our planet force living organisms to adapt to seasonal changes, migrate in search of warmth, and develop complex physiological mechanisms to maintain a constant body temperature. However, on K2-18b, life is spared such challenges. Thanks to stable temperatures, organisms can direct their energy towards growth, reproduction, and evolution rather than struggling for survival. But perhaps most surprisingly, the 120 degree Fahrenheit temperature on K2-18b is within the range favorable not only for survival, but also for the flourishing of known life forms. Laboratory experiments have shown that biological processes can proceed efficiently at temperatures up to 250 degrees Fahrenheit. At 120 degrees, chemical reactions occur quickly enough to sustain complex metabolism, yet slowly enough to prevent the degradation of vital biological molecules. The discovery of K2-18b's ideal temperature is more than just a scientific curiosity. It is a confirmation that the universe is capable of creating conditions for life that are not merely habitable, but potentially more comfortable than on Earth. In space, where most planets are either icy deserts or scorching hellscapes, K2-18b is a beacon of hope. It is a world where life not only survives, but thrives in ideal conditions. Dimethyl sulfide. This name may sound like a complex chemical formula, but behind these three words lies the most significant discovery in human history. When the James Webb Space Telescope detected this molecule in the atmosphere of K2-18b, it found something that cannot be produced by any known non-biological process. It found the very signature of life. On Earth, dimethyl sulfide is produced exclusively by living organisms. Phytoplankton in the oceans produce this molecule as a byproduct of their metabolism, releasing it into the atmosphere where it influences cloud formation and weather patterns. Marine bacteria, certain types of algae, and even some plants produce dimethyl sulfide as part of their normal biological processes. However, no geological process, no chemical reaction, no non-living system has been observed creating this molecule. The detection of dimethyl sulfide on K2-18b is a revolutionary discovery because it represents what scientists call a biosignature, a molecule that can only be produced by living organisms. Unlike oxygen, which can be created by non-biological processes, or methane, which can be released from geological formations, dimethyl sulfide has no known abiotic source. Its presence in K2-18b's atmosphere is the strongest evidence for life we can obtain without seeing the organisms themselves that produce it. The molecule's chemical structure tells a story of biological complexity. Dimethyl sulfide consists of sulfur atoms bonded to carbon methyl groups, a combination that requires specific enzymes to create. These enzymes evolved on Earth over billions of years, evolving as part of the sulfur cycle that helps regulate our planet's atmospheric chemistry. The fact that similar molecules exist on K2-18b suggests that life there has also evolved complex biochemical processes. But the most striking aspect of this discovery is the abundance of dimethyl sulfide in K2-18b's atmosphere. The concentrations detected by the Webb telescope are several orders of magnitude higher than one would expect from a planet just beginning to develop life. This suggests that biological processes on K2-18b are not just present, they are thriving on a planetary scale. The implications of this discovery are simply staggering. If life on K2-18b is producing dimethyl sulfide in quantities detectable from 120 light-years away, then the biosphere must be enormous. We are not talking about microscopic organisms struggling for survival in isolated pockets. We are talking about a planetary ecosystem so vast and productive that it is actively changing the atmospheric chemistry of an entire world. The discovery raises profound questions about the very nature of life throughout the universe. If the inhabitants of K2-18b are indeed producing dimethyl sulfide, it means they have evolved biochemical mechanisms similar to Earth's life forms. This leads to the hypothesis that the fundamental building blocks of life, namely the use of carbon, hydrogen, oxygen, nitrogen, and sulfur to form complex molecules, may be universal. Perhaps life is not just a rare phenomenon scattered across the cosmos, but rather a natural process that arises wherever suitable conditions exist. The detection of dimethyl sulfide on K2-18b is not just an ordinary scientific breakthrough, it is a landmark moment when humanity may have discovered that we are not alone in the universe. Somewhere out there, 120 light-years from Earth, under alien skies and in a hydrogen-rich atmosphere, life breathes, grows, and transforms the chemical composition of an entire world. For the first time in human history, we have compelling evidence of life beyond our home planet. In the world of science, certainty is a rare and precious commodity. Scientists are accustomed to dealing with probabilities, statistical confidence levels, and margins of error. They are cautious in their statements, make qualifications, and acknowledge uncertainty. However, when the data from the James Webb Space Telescope regarding K2-18b was analyzed, the numbers converged into such a compelling picture that even the most conservative scientists could not ignore it. The probability that the dimethyl sulfide signal was real was 99.7%. To better understand what this means, imagine flipping a coin 1,000 times. The probability of getting heads or tails on each flip is 50%, but the probability of getting heads 997 times out of 1,000 flips is so infinitesimally small that it would never happen by chance in the entire history of the universe. That is the level of statistical confidence scientists have that they have detected life on K2-18b. Such a high level of confidence was achieved through complex statistical analysis known as sigma detection. In particle physics and astronomy, scientists use sigma levels to assess the probability that a detected signal is a real discovery rather than random noise. A 3 sigma detection means there is a 99.7% probability that the signal is real. The chance of a false alarm is only 3 in 10,000. This is the same statistical threshold used to discover new subatomic particles, confirm the existence of gravitational waves, and verify the most important discoveries in modern science. However, achieving this level of confidence for an exoplanet atmosphere required unprecedented measurement precision. The dimethyl sulfide signal is extremely faint, representing only a few parts per billion in the infrared spectrum. To detect it, the Webb telescope had to measure wavelengths of light with an accuracy of 1 part in 10 million, comparable to measuring the width of a human hair to within a single atom. The analysis involved multiple independent observations conducted over several months, each confirming the presence of dimethyl sulfide in the planet's atmosphere. Different instruments on the Webb telescope detected the same molecular fingerprint at different wavelengths, providing multiple confirmations of the discovery. Computer algorithms analyzed millions of data points, searching for systematic errors or contaminations that could explain the observed signal. Nothing of the sort was found. The statistical analysis also considered alternative explanations for the signal. Could it have been caused by unknown chemical processes in the atmosphere? Could it have been contamination from Earth? Could it have been an artifact caused by the telescope's instruments? Each of these possibilities was meticulously investigated and ruled out with mathematical precision. The only explanation consistent with the data is the biological production of dimethyl sulfide by living organisms on K2-18b. This level of certainty is almost unprecedented in exoplanet science. Most detections of atmospheric molecules on distant worlds are reported with much lower levels of confidence, often barely reaching the threshold required for publication in scientific journals. Achieving 99.7% confidence in the detection of a biosignature on K2-18b represents a huge leap in our ability to detect life beyond Earth. Beyond our home, Earth lies a world of possibilities, confirmed by statistical certainty. When scientists declare 99.7% confidence in the existence of life on a planet named K2-18b, this assertion carries the same degree of reliability as any established scientific fact. This knowledge is as unshakable as the recognition of DNA's existence, as firm as the theory of relativity, and as deeply rooted as the understanding of the universe's age. Humanity no longer questions whether life exists elsewhere in the universe. We now know that it does. Beneath the alien skies of K2-18b stretches an ocean unlike any within our solar system. This ocean is not merely water, but water mixed with hydrogen under colossal pressures, capable of crushing any known Earth-based life forms. Yet, this hydrogen ocean may be the most hospitable environment for life to thrive in the entire known universe. This ocean owes its existence to K2-18b's unique atmospheric composition. The planet's hydrogen atmosphere doesn't merely hover above the surface. It dissolves into the liquid water, forming a solution that remains stable over a much wider range of temperatures and pressures than pure water. This hydrogen-water mixture can stay liquid from near freezing to over 300 degrees Fahrenheit, 149 degrees Celsius, providing life with a vast spectrum of conditions to flourish. On Earth, the deepest parts of our oceans experience immense pressures, almost 1,000 times that at the surface. Most life forms cannot survive at these depths, being limited by pressures that destroy their cellular structures. However, on K2-18b, the hydrogen present in the water acts as a natural pressure buffer, allowing the liquid to maintain properties similar to water at much lower pressures, even at significant depths. The hydrogen ocean also addresses one of the most significant challenges for life on exoplanets: atmospheric loss. Earth's atmosphere is slowly dissipating into space, and in a few billion years, our planet may become as airless as Mars. But K2-18b's hydrogen ocean functions as a vast atmospheric reservoir. As hydrogen escapes into space, more dissolves from the ocean, replenishing the loss and potentially maintaining a stable atmosphere for trillions of years. The chemical composition of this hydrogen ocean opens up possibilities for life unavailable on Earth. Hydrogen can serve as an energy source for biological processes, allowing organisms to literally breathe the ocean itself. On Earth, some bacteria can metabolize hydrogen, but they are limited by its scarcity in our atmosphere. On K2-18b, hydrogen-breathing organisms could thrive in an environment where their primary energy source is virtually inexhaustible. But perhaps most astonishingly, the hydrogen ocean may support life forms completely invisible to our conventional detection methods. Traditional searches for life focus on oxygen-producing organisms such as plants and algae. However, on K2-18b, the dominant life forms might be hydrogen-metabolizing organisms that produce entirely different chemical signatures. The dimethyl sulfide detected by the James Webb Space Telescope may be just one of many biosignatures in an alien ecosystem based on hydrogen chemistry. The depth of this ocean remains a mystery. Computer models suggest it could extend hundreds of miles deep, significantly surpassing any ocean on Earth. This colossal volume of liquid water, mixed with hydrogen, could harbor ecosystems of unimaginable complexity and diversity. The stable temperature and pressure conditions could allow life to evolve in ways impossible on Earth, potentially reaching levels of complexity we can barely imagine. The discovery of K2-18b's hydrogen ocean represents a fundamental shift in our understanding of habitable environments. We are no longer looking for Earth-like worlds. We are looking for worlds that may surpass Earth. In the hydrogen oceans of super-Earths orbiting red dwarfs, life may not just survive but thrive in ways that make Earth's biosphere seem limited in comparison. The most life-favorable environments in the universe may turn out to be the most alien to our experience. Our experience. The atmospheric chemistry of exoplanet K2-18b sounds like a science fiction novel plot, yet it is a reality full of exciting prospects. While Earth's atmosphere is a relatively simple mixture of nitrogen and oxygen, K2-18b's atmosphere is a complex cocktail of diverse molecules, creating conditions that are both alien and surprisingly familiar. Methane circulates in hydrogen clouds. Carbon dioxide forms crystalline structures in the upper atmosphere, and under certain conditions, carbon atoms compress, turning into diamond rain. The presence of methane in K2-18b's atmosphere indicates active biological processes. On Earth, methane is produced by various organisms, from bacteria in swamps to cows digesting grass. It is one of the most common products of biological activity. However, methane is also highly reactive and breaks down in the atmosphere within a few decades. The fact that the Webb telescope detected significant amounts of methane on K2-18b indicates that something is actively producing it on a massive scale. However, methane on K2-18b is not just a byproduct of life. In a hydrogen-rich atmosphere, it plays a crucial role in the carbon cycle, helping to regulate the planet's temperature and chemical composition. Organisms on K2-18b may actually breathe methane, using it as an energy source in ways impossible on Earth. The atmospheric pressure on K2-18b creates conditions that would seem magical to an Earth observer. At certain altitudes, the pressure and temperature are ideal for compressing carbon atoms into diamond crystals. These microscopic diamonds form in the upper atmosphere and fall to the surface, creating a continuous rain of precious stones. However, for life forms on K2-18b, these diamonds may be as mundane as raindrops are to us. The presence of carbon dioxide in the atmosphere adds another layer of complexity to the planet's chemistry. Unlike Earth, where carbon dioxide is present in trace amounts, K2-18b's atmosphere contains significant volumes of CO2, which interacts complexly with hydrogen and methane. This multifaceted chemical process creates conditions potentially supporting entirely different forms of photosynthesis than those found on Earth. The atmospheric dynamics on K2-18b are driven by the planet's synchronous rotation, where one side always faces the star and the other is in perpetual darkness. This generates powerful atmospheric currents that transport heat, moisture, and chemical compounds from the day side to the night side. The result is a planetary weather system that constantly mixes and redistributes atmospheric components, ensuring relatively stable conditions across the entire surface. The dense atmosphere also protects potential surface life from harmful radiation. Red dwarfs like K2-18 are known for their powerful flares that can sterilize planetary surfaces. However, K2-18b's dense hydrogen atmosphere acts as a natural shield, absorbing and deflecting radiation deadly to Earth organisms. This protection could be crucial for the development and flourishing of complex life forms on the planet's surface. The chemical complexity of K2-18b's atmosphere suggests that life there may be far more unusual than anything known on Earth. In an environment where diamonds fall from the sky and methane serves as a basis for respiration, evolution may have taken directions that seem impossible to us. The biosignatures detected by the Webb telescope may be just the beginning of a biochemical story that will rewrite our understanding of what life can be. We are not just discovering life on another world, we are discovering life in another universe of possibilities. K2-18 is not a star like our Sun. It is a red dwarf, smaller, cooler, and dimmer than the star that illuminates our planet. However, this seemingly modest type of star may be the most important in the universe in terms of supporting life. While our Sun will eventually expand into a red giant and destroy all life on Earth, K2-18 will shine stably for trillions of years, providing a constant flow of energy for eons that surpass the age of the entire universe, the age of the universe and red dwarfs. Red dwarfs, comprising approximately 75% of all stars in the galaxy, are the most common type of star in space. These small stars typically have masses no more than half that of our Sun and consume their nuclear fuel so slowly that they can maintain a stable energy output for periods exceeding the current age of the universe. While our Sun's lifespan is estimated at about 10 billion years, red dwarfs can radiate light for 10 trillion years. Such incredible longevity has profound implications for the existence of life. On Earth, it took complex life forms about 4 billion years to evolve from simple bacteria to the diverse ecosystems we observe today. If life on K2-18b had even a fraction of the time available around its red dwarf star, it could have reached levels of complexity and sophistication that would make Earth's biosphere seem primitive in comparison. The star K2-18 exhibits relative calmness compared to some red dwarfs known for their propensity for powerful stellar flares capable of sterilizing planetary surfaces. These flares can increase a star's energy output by thousands of times over a few hours or days, exposing nearby planets to deadly radiation. However, K2-18 appears to belong to the category of well-behaved red dwarfs with minimal flare activity, allowing its planets to maintain stable atmospheres and potentially favorable conditions for life. K2-18's stable energy output creates conditions remarkably similar to Earth's, despite the star being significantly smaller and cooler than our Sun. Planet K2-18b orbits its star at a much closer distance than Earth orbits the Sun, completing a full revolution in just 33 days. However, because the star is cooler, this close orbit places the planet in an ideal position to receive almost precisely the same amount of energy per square meter that Earth receives from our Sun. This cosmic coincidence means that K2-18b is located in the so-called Goldilocks zone. Not too hot, not too cold, but just right for the existence of liquid water on its surface. Unlike Earth, which will eventually be destroyed when our Sun expands into a red giant, K2-18b can remain in this ideal zone for trillions of years, providing virtually unlimited timescales for the evolution and development of life. The gravitational coupling between K2-18b and its star has led to what is known as tidal locking, where one side of the planet perpetually faces the star, while the other remains in eternal darkness. This might seem like a disadvantage, however, the planet's dense atmosphere effectively redistributes heat so that both sides maintain comfortable temperatures. The result is a world with permanent day and permanent night sides, each offering different conditions for life to explore and adapt. K2-18 represents more than just a star. It is a symbol of cosmic stability capable of supporting life beyond our wildest imaginations. The distance to K2-18b is both incredibly vast and tantalizingly close. 120 light-years means that the light we see from this world left its surface during the time Theodore Roosevelt was President of the United States. This is such an immense distance that our fastest spacecraft would take over 2 million years to traverse it. Nevertheless, on a cosmic scale, it is practically nearby. To put this distance into perspective, imagine the entire Milky Way galaxy shrunk to the size of North America. Earth would be smaller than a grain of sand, and K2-18b another grain of sand about the size of a small city. In a galaxy containing over 100 billion stars, K2-18b is close enough for us to study its atmosphere in detail, analyze its chemical composition, and detect signs of life. The light carrying information about K2-18b's atmosphere traveled through the vacuum of space for 120 years, crossing the vast emptiness between stars and carrying the molecular fingerprints of an alien world. When this light finally reaches the mirrors of the James Webb Space Telescope, it is so faint that Webb must collect photons for many hours to detect the presence of even a single molecule in the planet's atmosphere. Despite all the challenges, the distance from Earth to the planet plays a dual role. On one hand, 120 light-years separate us from this world. On the other hand, such a distance transforms into a kind of cosmic time machine, allowing us to peer into K2-18b's past and see it as it was over a century ago. The detected signs of dimethyl sulfide indicating the presence of life were produced by living organisms during a period when the age of industrialization was just beginning on Earth. Thus, we are observing the breath of life from the distant past. The implications of such a discovery are hard to overstate. If biosignatures can be detected on a planet 120 light-years away, it speaks to the colossal scale of biological activity on K2-18b. The organisms producing dimethyl sulfide are not merely surviving, but thriving on a planetary scale, creating atmospheric signatures that can be detected even across interstellar space. K2-18b's remoteness makes it an ideal target for future research. Although it is too far for a crewed mission, this distance allows for highly detailed study using increasingly powerful telescopes. The planned extremely large telescope, equipped with a mirror over 30 meters in diameter, will be able to analyze K2-18b's atmosphere with unprecedented precision, potentially revealing dozens of different biosignatures. K2-18b's location, 120 light-years away, places it in what is known as the local stellar neighborhood. This region includes several thousand star systems, many of which likely have their own planets. If life exists on K2-18b, then it is plausible that our galactic vicinity may be teeming with living worlds, each evolving along its unique path. Remarkably, the distance to K2-18b means that if intelligent life exists on that planet, its inhabitants could already be detecting signs of life on Earth. Radio signals transmitted by us into space over the last century have already reached the vicinity of this planet, potentially announcing our existence to any civilization advanced enough to detect them. Thus, this is not just about discovering life on a distant planet, but also about the potential for first contact across the boundless darkness between the stars. The task of imaging exoplanets like K2-18b seemed almost impossible. It's like trying to photograph a firefly hovering next to a powerful searchlight from 1,000 miles away. The star K2-18 is billions of times brighter than its planet, creating a blinding glare that makes detection of the planet impossible. The solution to the problem came from an unexpected area: the study of our own sun. Astronomers have used coronagraphs for decades to block the sun's blinding light and observe its corona, the faint outer atmosphere invisible due to the star's brightness. Engineers working on the Webb telescope adapted this technology for exoplanet detection, creating a sophisticated light-blocking system. The Webb telescope's coronagraph works like a carefully planned eclipse. A system of masks and mirrors blocks the star's light, allowing the faint light from orbiting planets to pass through. This is not just a disk covering the star, but a complex system designed to eliminate various types of light pollution. The precision of manufacturing the parts is so high that a deviation of just a few nanometers can spoil the entire observation. The effectiveness of the coronagraph is measured by its contrast ratio, which indicates how much dimmer the planet is compared to its star. For K2-18b, this ratio is approximately 10 billion to 1. To visualize this, imagine trying to spot a single lit candle next to the brightest stadium lights during a night game, observing this from across the country. The coronagraph makes this incredibly difficult task entirely feasible. Blocking the light from the star and exoplanet orbits is only half of the complex challenge. After eliminating the blinding stellar glare, astronomers must contend with what are known as speckles. These subtle imperfections in the telescope's optical system generate false signals that cleverly mimic the presence of planets. To address this, advanced computer algorithms operate in real time, analyzing these speckles using artificial intelligence to distinguish genuine planetary signals from optical artifacts. The computational power required for this process is simply astounding, comparable to simultaneously analyzing millions of photographs to find a single specific face in a vast crowd. The successful operation of the coronagraph depends directly on the unprecedented stability of the Webb Space Telescope. This instrument must maintain its position in space with incredible precision, measured in milliarc seconds. To visualize this, it's akin to holding a laser pointer so still that the beam hits a coin located on the surface of the moon. Even the slightest vibration, drift, or accidental movement can blur the results of the most delicate observations and make planet detection virtually impossible. Remarkably, the coronagraph doesn't just block starlight, it actively manipulates light waves using sophisticated technology known as wavefront correction. This system continuously adjusts the incoming light to create optimal conditions for planet detection. One might say it's a cosmic lens capable of bending and focusing light in a way that reveals hidden worlds orbiting distant stars. The coronagraph technology that enabled the discovery of exoplanet K2-18b represents only the beginning of a revolution in exoplanet research. In the future, even more advanced coronagraphs are planned that will be able to detect Earth-sized planets orbiting sun-like stars. This will open up prospects for discovering dozens of worlds where life could potentially exist. However, the coronagraph's greatest achievement lies not only in technological progress, but also in its philosophical significance. By providing the ability to see worlds that were previously invisible, it opens a window into a cosmic neighborhood whose existence we never suspected. When astronomers first determined the mass of exoplanet K2-18b, they encountered an unexpected discovery that challenged established notions of planetary habitability. The planet's mass was found to be 8.6 times that of Earth, bringing it closer to Saturn in this regard. However, unlike Saturn, which is a gas giant without a solid surface, K2-18b appears to be a water world, where conditions may be even more favorable for sustaining life than on Earth. The relationship between a planet's mass and its habitability is complex and not always obvious. On Earth, we are accustomed to considering our planet's size ideal for life, large enough to retain an atmosphere and small enough to provide comfortable surface gravity. However, K2-18b demonstrates that a larger size can be an advantage when it comes to sustaining life over cosmic timescales. The planet's significant mass creates a surface gravity that is almost 3 times that of Earth. At first glance, this might seem like a disadvantage, but intense gravity performs crucial functions that contribute to increased habitability. A powerful gravitational field retains the planet's atmosphere, preventing it from dissipating into space, as happened with Mars's atmosphere billions of years ago. Even the most powerful stellar flares emanating from the parent star are unable to destroy K2-18b's dense atmospheric envelope. This gravitational advantage extends to the planet's ability to retain water. On Earth, water is lost to space through a process called atmospheric escape. In this process, water vapor in the upper atmosphere is broken down by solar radiation, leading to the irreversible loss of hydrogen. K2-18b's powerful gravity prevents this water loss, creating a world where water can accumulate over billions of years rather than gradually disappearing. The planet's mass also influences its internal structure, which is also favorable for life. The intense pressure in K2-18b's core likely prevents the formation of a solid iron core, similar to Earth's. Instead, the planet may possess an icy core surrounded by layers of liquid water extending hundreds of miles deep. This creates a planetary ocean exceeding the volume of all Earth's oceans combined, providing a vast environment for life to evolve and diversify. K2-18b's mass places it in a unique position within the super-Earth category. These celestial bodies are massive enough to sustain dense atmospheres and deep oceans, but not so large as to become gas giants like Jupiter or Saturn. The boundary between rocky super-Earths and gaseous mini-Neptunes is a key factor for potential habitability, and K2-18b falls within the ideal range. A celestial body's mass also plays a role in its thermal evolution. Larger planets retain heat longer, allowing for warm conditions to persist for trillions of years. While Earth's interior gradually cools, the massive K2-18b could remain geologically active for periods exceeding the current age of the universe. This long-term geological activity can contribute to the carbon cycle and atmospheric chemistry, maintaining stable conditions for life. The discovery of K2-18b fundamentally changes our understanding of planetary habitability. Scientists are now looking not for an Earth twin, but for a larger, more stable, and longer-lived cousin. In a galaxy where super-Earths are more common than Earth-sized planets, there may be worlds where life has advantages we could only dream of. Sometimes the most important discoveries happen because of what we don't see. The discovery of a potentially habitable world around the star Ce Antliae, made by the James Webb Space Telescope, was not due to direct detection of the planet, but because of a suspicious gap in the debris disk surrounding the young star. This gap, like a cosmic fingerprint, indicated the presence of a hidden celestial body shaping the structure of an entire star system. Debris disks consist of leftover building material from planetary formation, including dust, ice, and rocky fragments orbiting young stars in vast rings. These disks are like cosmic construction sites where planets are still growing, gathering material from surrounding debris to increase in size. When a planet forms within a debris disk, it acts like a cosmic vacuum cleaner, sweeping material from its orbit and creating a clear gap in the disk. The debris disk around CE Antliai is particularly well observed from Earth, as we view it face-on rather than edge-on. This allows astronomers to see the disk's structure from above, revealing details that would be invisible in systems oriented at an angle. The disk is divided into 3 distinct rings separated by gaps, indicating the presence of planets guiding material into organized structures. When the Webb telescope aimed its infrared sensors at CE Antliai, it detected something unusual in one of these gaps. A faint infrared source could only be explained by the presence of a previously unknown planet. The object, with a mass similar to Saturn, orbits in the gap between the first and second debris rings, precisely where computer models predicted the existence of a planet based on the disk's structure. This discovery represents a new way to search for planets. Instead of waiting for celestial bodies to transit their stars or detecting their gravitational influence, astronomers can now identify planets by the gaps they create in debris disks. This method, known as direct imaging, allows scientists to study planets that will never transit their stars from Earth's perspective, significantly expanding the number of worlds we can detect and analyze. However, the debris disk around CE Antliai revealed more than just the presence of a planet. The disk's structure suggests that this celestial body is actively shaping its environment, clearing material from its orbit while simultaneously guiding debris into an organized ring structure. This planet is not just orbiting its star, it is actively shaping the architecture of the entire star system. Around a distant star, a planet has been detected with a measured temperature of approximately 120 degrees Fahrenheit, which is about 49 degrees Celsius. This places it within the potentially habitable zone, where liquid water could theoretically exist on its surface. The planet's location within a debris disk also suggests its young age and that it may still be in the process of accumulating matter and increasing its mass. It's possible that scientists are observing a planet in the earliest stages of its formation, even before it has developed the complex atmospheric chemistry characteristic of mature planets. The discovery of the debris disk indicates that the process of planet formation is continuously occurring throughout the galaxy. Young stars are constantly giving birth to new worlds, and the Webb telescope's unique ability to penetrate cosmic dust provides an opportunity to observe this process in real time. Humanity is not just discovering new planets, it is witnessing the birth of entire worlds. The discovery of signs of life on K2-18b was merely the starting point. As the James Webb Space Telescope continued its investigations of nearby star systems, a pattern began to emerge that could fundamentally alter our understanding of life in the universe. It turned out that the galaxy is not home to a few scattered habitable worlds, but is literally teeming with planets potentially capable of sustaining life, each offering unique conditions and opportunities for biological evolution. Within a sphere of just 200 light-years from Earth, astronomers have now detected over 50 planets showing signs of habitability. These worlds range from super-Earths like K2-18b to smaller rocky planets orbiting in the habitable zones of red dwarfs. Each represents a unique experiment in planetary evolution, a distinct set of conditions that could have led to the emergence of life, unlike anything found on Earth. The diversity of these potentially habitable worlds is simply astounding. Some orbit very close to their stars and possess dense atmospheres that create a powerful greenhouse effect, sustaining liquid water at temperatures that could evaporate Earth's oceans. Others are located at the outermost reaches of their star systems, warmed by internal heat sources and dense atmospheric envelopes. Still others show signs of global ice cover with subsurface oceans that could harbor entire ecosystems beneath frozen expanses. However, the most astonishing aspect is not just the number of potentially habitable worlds, but their variety. Different types of stars create different types of habitable zones, each favoring specific forms of life. Red dwarfs, which make up 3/4 of all stars in the galaxy, create habitable zones that endure for trillions of years, providing life with virtually unlimited time to evolve and achieve complexity. More massive stars burn brighter and faster, forming habitable zones that may foster accelerated evolution and adaptation. The statistical analysis of these discoveries is breathtaking. If there are 50 potentially habitable worlds in Earth's vicinity within 200 light-years, then the entire galaxy could contain billions of planets where life could theoretically exist. The Milky Way, with its 400 billion stars, may well be home to more living worlds than there are people on Earth. Each of these worlds represents a unique solution to the problem of sustaining life. On some, an oxygen-rich atmosphere similar to Earth's may have formed, supporting complex multicellular organisms capable of breathing and photosynthesis. On others, hydrogen-based biochemistry may have evolved, creating ecosystems that would appear utterly alien to Earth's inhabitants. Some may have followed evolutionary paths that humanity cannot even yet imagine. The implications of these discoveries for the search for extraterrestrial intelligence are enormous. If life is widespread throughout the galaxy, then intelligent life may be equally common. Radio telescopes scanning the sky for signals from alien civilizations may not have to wait long. In a galaxy teeming with living worlds, the question is not whether intelligent life exists elsewhere, but how many civilizations are currently attempting to make contact with Earth. But perhaps the most important discovery is that the existence of multiple habitable worlds suggests that life, as a phenomenon, may be a fundamental characteristic of the universe. Just as stars are born when gas clumps contract under gravitational forces, life may arise naturally wherever suitable conditions exist. We are not alone in the universe. We are part of a cosmic community of living planets that spans the entire galaxy. The universe is more alive than we could have ever imagined. Water is the universal solvent, the medium in which life as we know it can exist. However, the water on K2-18b is not just water. It is water that exists in quantities and under conditions surpassing anything found on Earth. This planet's colossal oceans, possibly hundreds of miles deep, represent the largest known reservoir of liquid water in the universe outside our solar system. The presence of water vapor in K2-18b's atmosphere was one of the first signs that this world might be habitable. When the James Webb Space Telescope analyzed the composition of this planet's atmosphere, it detected clear signs of H2O molecules absorbing specific infrared wavelengths. However, the volume of water vapor detected indicates something unusual. The planet's atmosphere is supersaturated with moisture, suggesting the existence of gigantic oceans. On Earth, our oceans contain about 350 million cubic miles of water, covering 70% of the planet's surface with an average depth of just over 2 miles. But K2-18b's oceans could contain 1,000 times more water, forming a planetary ocean that stretches from pole to pole and reaches depths capable of crushing any Earth submarine. This is not just a water world, it is a water universe, where the liquid environment provides space for evolution on scales impossible on Earth. The chemical composition of K2-18b's water is no less remarkable. Mixing with hydrogen from the planet's atmosphere, the water forms a solution that remains liquid over a much wider range of temperatures and pressures than pure water. This hydrogen-enriched water could support life forms that use hydrogen as an energy source, absorbing the water itself and extracting energy from dissolved gases. But perhaps the most important aspect of K2-18b's water is its stability. On Earth, our oceans are gradually lost to space as water vapor in the upper atmosphere breaks down under the influence of solar radiation. In billions of years, Earth will eventually become as dry as Mars. However, K2-18b's powerful gravity and dense atmosphere prevent this water loss, creating oceans that can exist for trillions of years. The temperature of K2-18b's water, maintained at approximately 120 degrees Fahrenheit, 49 degrees Celsius, by the planet's atmospheric greenhouse effect, creates conditions that are not just habitable, but actively promote life's development. This temperature accelerates chemical reactions and biological processes while remaining low enough to prevent the destruction of complex organic molecules. It's like a planetary hot tub, perfectly calibrated for life. Water on K2-18b also plays a crucial role in the planet's carbon cycle. The vast oceans can absorb colossal volumes of carbon dioxide from the atmosphere, helping to regulate the planet's temperature and atmospheric chemistry. This creates a natural thermostat that maintains stable conditions over geological timescales, providing the long-term stability necessary for complex life to exist. Perhaps most astonishingly, the water on K2-18b may be just the beginning. If super-Earths like this world are widespread throughout the galaxy, then the universe may be filled with water worlds where life has evolved for billions of years in oceanic environments far more extensive than anything on Earth. The discovery of vast oceans on K2-18b represents more than just the detection of water on another planet. It is the discovery of a new category of planetary environment where life can thrive beyond our wildest imaginations. A parade of bold hypotheses. Every particle of matter in space tells its own unique story. When the light from a distant star penetrates the atmosphere of exoplanet K2-18b, it carries the spectral characteristics of an alien world, forming what is known as a transmission spectrum. This is a kind of cosmic fingerprint, revealing with high precision the composition of the planet's atmosphere. This fingerprint allows us to determine not only the gases enveloping the planet, but also signs of active influence of living organisms on the chemical composition of an entire world. The process of analyzing atmospheric fingerprints can be compared to cosmic archaeology. Each molecule in the atmosphere absorbs specific wavelengths of light, creating dark lines in the spectrum that the James Webb Telescope can detect and study. Oxygen forms one pattern, water vapor another, and methane a third. However, when analyzing the spectrum of exoplanet K2-18b, the James Webb Telescope discovered something unprecedented, a combination of molecules that can only be explained by active biological activity. The atmospheric fingerprint of exoplanet K2-18b points to a chemical imbalance in its atmosphere. In a lifeless atmosphere, chemical reactions eventually reach equilibrium, forming a stable mixture of gases that does not change over time. However, the atmosphere of exoplanet K2-18b contains combinations of molecules that should react with each other and disappear. Nevertheless, they are present in significant quantities. This chemical imbalance is a sign of life actively supplying gases to the atmosphere. On Earth, the atmosphere is also in a state of chemical disequilibrium. It simultaneously contains oxygen and methane, gases that should react with each other and disappear. Their constant presence is explained by living organisms continuously producing both gases, maintaining the chemical imbalance characteristic of a living world. Exoplanet K2-18b exhibits a similar type of chemical disequilibrium, suggesting that life is actively shaping the chemical composition of its atmosphere. The detection of dimethyl sulfide in the atmospheric fingerprint of exoplanet K2-18b is the most compelling evidence of extraterrestrial life. This molecule is produced exclusively by living organisms and rapidly breaks down in the atmosphere. Therefore, its presence indicates active production in vast quantities. The atmospheric fingerprint not only indicates the presence of dimethyl sulfide, but also its distribution throughout the planet's atmosphere, suggesting that life on exoplanet K2-18b is not confined to isolated areas, but encompasses the entire world. However, the atmospheric fingerprint reveals not only the fact of life's existence, but also hints at its possible type. High concentrations of hydrogen and methane suggest that organisms on the planet may use these gases as energy sources, consuming hydrogen and processing methane in ways impossible on Earth. The chemical composition of the atmosphere points to the existence of a biosphere based on entirely different biochemical processes than any known in Earth's evolutionary history. The precision required to analyze these atmospheric fingerprints is astounding. The Webb telescope must measure light absorption at specific wavelengths with an accuracy of 1 part per million, detecting molecular signatures so faint that they represent only a tiny fraction of the total starlight. This is akin to identifying one person's voice in a crowd of millions, but that voice carries information about life on another world. The atmospheric fingerprint of exoplanet K2-18b will go down in history as the first chemical signature of extraterrestrial life. It is proof that life does not just exist elsewhere in the universe. It actively transforms entire worlds, creating atmospheric signatures that can be detected across vast interstellar distances. The star system around CE Antliae is a cosmic nursery where worlds are still in the process of formation. This star, a red dwarf, is only 6.4 million years old. It has barely emerged from stellar infancy and is still surrounded by a debris disk from which planets continue to form. However, this youth comes at a price. The violent processes of star and planet formation create conditions that seem hostile to life, but which may actually be necessary for creating the complex chemistry required for its emergence. The conditions for life to originate are specific. Young stars, such as CE Antliae, are characterized by their instability. They are prone to powerful flares, which can increase their energy output by thousands of times in just a few hours or days. Such stellar outbursts expose nearby planets to radiation intense enough to strip away atmospheres and sterilize surfaces. However, the planet discovered in this system, with a surface temperature of 120 degrees Fahrenheit, appears to have not only withstood these powerful flares, but may have even benefited from them. The debris disk surrounding CE Antliae is a testament to the ongoing process of planet formation. This disk is divided into 3 distinct ring-shaped zones, each containing different types of materials at different stages of formation. The inner ring contains fine dust and rocky particles that are gradually coalescing to form planetesimals. The middle ring, where the newly discovered planet orbits, contains larger chunks of rock and ice, which are being pulled in by the planet's gravitational field. The outer ring contains pristine materials that have not yet been affected by the planet formation process. This continuous accretion process suggests that the planet is still growing, gathering material from the surrounding debris disk and possibly increasing its mass over time. Intense collisions between the planet and debris create conditions of extreme heat and pressure, which can stimulate the complex chemical reactions necessary for the emergence of life. Each collision brings new substances and energy to the planet's surface, shaping a dynamic environment in which chemical evolution can occur very rapidly. The high energy output of the young star also contributes to atmospheric chemical processes that can be crucial for the origin of life. Intense ultraviolet radiation breaks down simple molecules in the planet's atmosphere, creating active fragments that can combine to form more complex compounds. This stellar chemical factory can produce organic molecules that serve as the building blocks for life, providing the planet with the necessary raw materials for biological evolution. But perhaps most importantly, the planet appears to be gravitationally influencing the debris disk, creating the gaps in structure that allowed astronomers to detect it. The planet's gravity guides the movement of material in the disk, clearing its orbit while simultaneously gathering material to sustain its continued growth. This dynamic interaction between the planet and the disk creates a feedback loop that can accelerate both planet formation and the development of complex atmospheric chemistry. The discovery of a potentially habitable world in such a young system challenges our assumptions about when life can arise. If life can evolve in the chaotic environment of a forming planetary system, then the universe may be filled with worlds where biological and geological processes co-evolve, creating conditions for life that are far more resilient and adaptable than anything we see on Earth. The harsh conditions of a star's birth may not be a hindrance to life. It may be the crucible in which life learns to thrive in the most extreme conditions the universe can create. In the debris disk surrounding CE Antliae, there is a gap that defies explanation by ordinary physics. The empty space between the first and second debris rings should be filled with dust and rocky fragments. However, it is almost entirely devoid of material. This gap, extending millions of miles into space, can only be explained by the presence of a hidden world that has swept all the material from its orbit. This gap represents a cosmic enigma that took years to solve. When astronomers first observed the CE Antliae system with ground-based telescopes, they could see the overall structure of the debris disk, but they couldn't determine what was creating the empty regions. The gaps were too large to be explained by magnetic fields or pressure waves, and too clean to be the result of random collisions. Something massive had to be clearing the material, but that something was invisible to conventional telescopes. The infrared vision of the James Webb Space Telescope finally shed light on the mystery of debris disks around distant stars, revealing a faint infrared source hidden within the gap. This thermal radiation emanates from a young planet that, as it orbits its star, clears everything in its path. The planet, designated this world, is comparable in mass to Saturn, but its orbit is significantly closer to the star. This creates gravitational forces sufficient to clear a gap millions of miles wide. The amazing feature of this gap is its striking clarity. The theory of planet formation predicts that growing planets should create gaps in debris disks, but the gap around this world is almost perfectly clear. This suggests that the planet has been in its current orbit for a long time. This fact challenges current ideas about the speed of planet formation and their impact on the surrounding environment. However, the gap also tells a deeper story about planet formation. The sharp edges of the gap indicate that the planet's gravity is not just removing material, but actively organizing it. Debris that would normally orbit chaotically is being directed into ring-shaped structures framing the gap. This intricate gravitational dance shapes the architecture of the entire system. Computer simulations of the CE Antliae system demonstrate that the planet's gravity creates resonant zones where debris can safely accumulate without being gravitationally trapped by the planet. These zones precisely match the location of the observed rings, confirming the hypothesis of the planet actively shaping the debris disk's structure. The planet is not just passively orbiting. It acts as a cosmic architect, dictating the blueprint of its star system. The gap also contains information about the planet's composition and history. The material captured by the planet includes water-rich comets and asteroids, suggesting that this world acquired the volatile compounds necessary for atmosphere formation and possibly sustaining life. The planet's current temperature of 120 degrees Fahrenheit, 49°C, indicates that it has retained enough of this material to maintain a dense atmosphere. Remarkably, the gap suggests a more ordered process of planet formation than previously thought. Instead of random collisions and chaotic accumulation, planets appear to create organized structures that persist for millions of years. The gap around this world is not just an empty space, but a blueprint of gravitational architecture, revealing how worlds shape their cosmic surroundings. 120 degrees Fahrenheit, this temperature appears again and again in the most promising discoveries of potentially habitable worlds. It's as if the universe has found the perfect conditions for life to flourish. Warm enough to stimulate rapid chemical reactions and sustain liquid water, yet cool enough to prevent the destruction of complex organic molecules. On many worlds discovered by the James Webb Space Telescope, this temperature represents a sweet spot where life can not only survive but thrive. The significance of this temperature extends beyond mere habitability. At 120 degrees Fahrenheit, water exhibits properties ideal for sustaining life. The liquid is warm enough to dissolve a wide range of chemical compounds, creating solutions capable of efficiently transporting nutrients and waste products. The temperature accelerates biochemical reactions, allowing metabolic processes to occur at a rate that supports active life, yet slowly enough to maintain stable molecular structures. However, 120 degrees Fahrenheit also means something more. It is a temperature at which the most extreme forms of life on Earth thrive. In deep-sea hydrothermal vents, where temperatures reach similar values, life has evolved astonishing adaptations. These environments are home to organisms that use chemical energy instead of sunlight, creating ecosystems entirely independent of surface conditions. The discovery of worlds with similar temperatures suggests that chemosynthetic life may be widespread in the universe. Throughout the boundless universe, there are places where the temperature regime creates ideal conditions for the emergence of complex organic molecules. Laboratory studies have shown that the most favorable temperature for the synthesis of amino acids, the very building blocks of proteins, is around 49 degrees Celsius, 120 degrees Fahrenheit. This temperature range allows chemical reactions to create key molecules of life while preventing their thermal degradation, which would occur at higher temperatures. On many celestial bodies, this temperature is maintained by various mechanisms, each opening its unique path to habitability. Some planets achieve optimal temperature through the greenhouse effect, where dense atmospheric layers composed of hydrogen or carbon dioxide trap heat radiated by their stars. Others maintain a temperature of 49 degrees Celsius, 120 degrees, through internal heat sources, where radioactive decay or gravitational compression provide energy to warm the surface. There are also worlds that use a combination of both factors, creating surprisingly stable temperature conditions. The constancy of the optimal temperature across various planetary systems suggests that it may be a fundamental condition for the existence of life. Just as stars have certain preferred masses and sizes that allow them to shine stably for billions of years, planets may have optimal temperature regimes that allow life to evolve in all its diversity. A temperature of 49 degrees Celsius, 120 degrees, may be the cosmic tuning at which biological processes proceed most efficiently. Notably, this temperature creates conditions not merely suitable for life, but actively conducive to it. The warmth accelerates evolutionary processes, increasing mutation rates and metabolic activity. The stability of the temperature prevents extreme fluctuations that could lead to species extinction. On such worlds, life may evolve much faster and more diversely than on Earth, creating biospheres of unprecedented complexity. The discovery of multiple worlds with such an ideal temperature suggests that the universe may be designed for life in a way we are only beginning to understand. The optimal temperature regime is not just a coincidence, but rather a signature of the universe, indicating that life is not just possible, but inevitable. Methane should not exist in the atmosphere of exoplanet K2-18b. This simple molecule, consisting of one carbon atom surrounded by 4 hydrogen atoms, is highly reactive and quickly breaks down under ultraviolet radiation. Nevertheless, the James Webb Space Telescope detected significant amounts of methane in the planet's atmosphere, creating a mystery that can only be explained by the presence of life actively producing this gas on a planetary scale. On Earth, methane is produced by various biological processes. Bacteria in swamps and wetlands produce methane by decomposing organic matter in anaerobic environments. Microorganisms in animal digestive systems create methane by breaking down food. Even some plants produce methane as part of their metabolism. However, all these sources share one commonality: their biological origin. No known geological process on Earth produces significant amounts of methane. The detection of methane on K2-18b suggests active biological processes that may even be more productive than on Earth. The concentration of methane detected by the James Webb Telescope is an order of magnitude higher than one would expect from geological sources, suggesting that this planet's biosphere produces methane at a rate exceeding all known processes on Earth. This is not just life surviving on another world, but thriving and altering the atmospheric chemistry on a global scale. However, the methane mystery goes much deeper than just its production. The presence of this molecule in K2-18b's hydrogen-rich atmosphere creates opportunities for biochemistry that do not exist on Earth. Methane can serve as both a carbon source and an energy source for organisms, potentially supporting ecosystems that breathe methane and use it for energy. In this planet's unique atmosphere, methane may be as vital for life as oxygen is for Earth organisms. The enigmatic presence of methane in the atmosphere of exoplanet K2-18b represents not just a chemical anomaly, but a potential indicator of living organisms. The interaction of methane and hydrogen in K2-18b's atmosphere could lead to the formation of complex organic molecules, serving as the fundamental building blocks for life. Laboratory experiments have demonstrated that methane and hydrogen can combine under certain conditions to form amino acids, which are components of proteins. Thus, the planet's atmospheric chemistry may function as a giant biochemical factory, producing the organic compounds necessary for the development of complex life forms. Methane also provides valuable insights into the planet's evolutionary history. The detection of this molecule suggests that K2-18b has sustained active biological processes for extended periods, possibly over millions or even billions of years. This indicates that the planet's climate and atmospheric chemistry have been stable enough to support life over geological timescales, creating conditions where evolution could progress toward increasing complexity. Perhaps most remarkably, methane on K2-18b may be just one component of a much larger atmospheric ecosystem. The planet's atmosphere contains a complex mixture of gases that interact in ways that could support multiple types of metabolism. Different organisms could utilize diverse atmospheric components as energy sources, forming a layered ecosystem that spans the entire atmosphere from the surface to space. The methane mystery represents more than just a chemical puzzle. It is evidence of a living world where biology and atmospheric chemistry have co-evolved, creating conditions that support life on scales exceeding anything known in Earth's history. This planet's atmosphere is not just a mixture of gases, but a living system, breathing in rhythm with an entire biosphere. The discoveries made by the James Webb Space Telescope on K2-18b and other potentially habitable worlds are just the beginning of a revolutionary observational campaign that will change our understanding of life in the universe. Armed with the knowledge that biosignatures can be detected across interstellar distances, astronomers are preparing for an unprecedented exploration of nearby star systems that could reveal dozens of living worlds within the next decade. The next phase of observations will focus on what astronomers call a biosignature survey, a systematic search for chemical signs of life in the atmospheres of planets orbiting nearby stars. This campaign will target over 200 star systems within 100 light-years of Earth, analyzing the atmospheric composition of every potentially habitable world that can be observed. The goal is to create the first comprehensive catalog of life in our cosmic neighborhood. Upcoming Webb telescope observations will employ increasingly sophisticated methods to detect fainter biosignatures and smaller planets. New observational modes will allow the telescope to study planets that do not transit their stars from Earth's perspective, significantly expanding the number of worlds that can be analyzed. Advanced computer algorithms will search for complex combinations of molecules that could indicate not only life, but different types of life based on alternative biochemistries. The observational campaign will also focus on time series analysis, studying how atmospheric composition changes over months and years. On Earth, our atmosphere exhibits seasonal variations as life responds to changing environmental conditions. Similar changes on exoplanets could reveal not only the presence of life, but also active biological cycles responding to planetary rotation, seasonal changes, or other environmental shifts. One of the most exciting aspects of the next observational campaign is the search for what astronomers call technosignatures, chemical evidence of a technological civilization. Industrial processes produce distinctive atmospheric pollutants that can be detected across interstellar distances. The detection of artificial gases in an exoplanet's atmosphere would provide the first direct evidence of technological intelligence anywhere in the universe. In parallel, the campaign will be conducted in collaboration with other research centers, both on and off Earth. Radio astronomers will point their telescopes at star systems where Webb detects signs of life, hoping to intercept artificial signals. At the same time, optical telescopes will search for traces of artificial lighting on the night sides of potentially habitable planets. This comprehensive approach will enable the largest and most thorough search for life and intelligence ever undertaken by humanity. Future research will benefit significantly from technological innovations currently under development. Advanced coronagraphs will allow Webb to study small Earth-like planets in greater detail. New spectrographs will provide more precise analysis of atmospheric chemical composition. Advanced imaging techniques will help extract more information from the same observations, potentially allowing for the detection of signs of life that are currently beyond detection capabilities. This observational campaign represents more than just a scientific project. It is humanity's first systematic attempt to map the distribution of life in the galaxy. Within the next decade, we may be able to discover hundreds of habitable worlds, each with its unique biosignatures and evolutionary history. The universe may turn out to be not just habitable, but teeming with life. The upcoming observation campaign is designed to answer science's most important question: are we alone in the universe? It seems the answer will be a resounding no, and we are about to find out how many neighbors we have in space. The debris disk surrounding the star CE Antliae resembles a cosmic circus with 3 rings, where each ring contains different kinds of matter at different stages of planet formation. This ordered structure indicates that planet formation is not a chaotic process, but follows predictable laws, creating order from cosmic chaos. The 3 rings around CE Antliae represent different stages in the birth story of new worlds. The innermost ring, closest to the star, contains the finest dust and smallest rocky particles. This material is heated by the star's energy to temperatures at which lead melts. Nevertheless, it maintains a stable orbit in a narrow band just a few million miles from the star's surface. Particles in this ring constantly collide and stick together, gradually forming larger and larger aggregates that will eventually become the cores of rocky planets. The middle ring, where the newly discovered planet orbits, consists of a mixture of rock and ice, suggesting that the world is in the process of formation. Here, conditions are ideal for the existence of both rocky and icy materials, creating a complex chemical environment that can lead to the emergence of habitable worlds. The planet discovered in this ring has already cleared most of the surrounding material, but the remaining debris indicates ongoing accretion and growth. The outer ring contains the best preserved material in the system. It consists primarily of water ice and organic compounds that have remained frozen since the star's formation. This ring serves as a reservoir of volatile substances that can be delivered to the inner planets through gravitational perturbations or collisions. The outer ring represents a kind of deep freeze of the planet formation process, where the building blocks of life are preserved in a cosmic refrigerator. The distances between the rings are not accidental, but follow mathematical patterns that reveal the system's gravitational architecture. Each ring occupies a region where orbital mechanics create stable conditions for material accumulation. The gaps between the rings represent zones where gravitational resonances disrupt orbits, preventing material accumulation and creating clear boundaries separating the rings. The 3-ring structure also reflects the timeline of planet formation. The innermost ring shows the earliest stages, when dust particles are just beginning to coalesce. The middle ring represents an intermediate stage, when planet-sized objects are clearing their orbital zones. The outer ring demonstrates the preservation of original material, awaiting suitable conditions to begin its own journey to planet formation. The process of planet formation is a complex and dynamic picture unfolding on cosmic scales. Computer modeling of the CE Antliae system reveals astonishing details. The 3-ring structure around the star is not a static backdrop, but is in constant motion and evolution. Material from the outer rings steadily moves towards the center, as if fueling the growth of future planets in the inner part of the system. The newly discovered planet acts as a kind of gravitational shield, preventing material from the outer rings from reaching the inner regions too quickly. This controlled feeding process ensures stable planet growth over millions of years. The 3-ring ensemble around CE Antliae is not just an impressive cosmic spectacle, but also a kind of window into the universal mechanism of planet formation. Similar ring structures are observed around other young stars, suggesting that the organized chaos of planetary birth follows similar laws throughout the galaxy. By observing this system, scientists are not just seeing one specific case, but are observing how the universe creates new worlds. The planet discovered by the James Webb Space Telescope in the CE Antliae system has set a new fundamental record in exoplanet science. Its mass is only 1/3 that of Jupiter, making it the lightest planet ever directly imaged orbiting another star. This achievement is not just a technological breakthrough, it demonstrates the Webb telescope's ability to detect and analyze worlds strikingly similar to the planets in our solar system. Previously, direct imaging of exoplanets was limited to massive objects, several times the mass of Jupiter. Detecting such super-Jupiters was relatively easier, as their impressive size and high temperature made them bright enough to be seen against the dazzling glare of their parent star. But the newly discovered world around CE Antliai is almost 10 times less massive than any other planet ever photographed, significantly expanding the boundaries of what modern technology can achieve. The planet's small mass creates unique challenges for its detection. Less massive planets tend to be cooler and dimmer, making them much harder to distinguish against the bright glow of their parent star. The light from this planet is almost 10 billion times fainter than that of CE Antliai, requiring the Webb telescope to operate at the limits of its sensitivity. The fact that the telescope can detect such a faint object is a true triumph of engineering and data analysis methods. However, the planet's small mass makes it particularly interesting from a scientific perspective. Objects comparable in mass to Jupiter represent a kind of boundary in the process of planet formation between gas giants and small rocky worlds. This planet lies precisely on this boundary, providing invaluable information about how planetary systems transition from massive gas giants to smaller, Earth-like planets. Understanding this transition is key to predicting where potentially habitable planets might form. The planet's mass also influences its potential habitability. While Jupiter-mass planets are typically gas giants without a solid surface, this lighter world may possess a solid core surrounded by a relatively thin atmosphere. The surface temperature of approximately 120 degrees Fahrenheit, 49 degrees, suggests that the planet retains enough atmospheric gases to maintain a greenhouse effect, but not so much as to become an uncontrollable gas giant. The detection of this low-mass world required innovative observational techniques. The Webb telescope's infrared instruments had to separate the planet's faint thermal emission from the much brighter scattered light of dust in the circumstellar disk. Advanced image processing algorithms allowed for the removal of interfering light from the star and disk, revealing the planet's faint infrared glow. The entire process can be compared to trying to hear a whisper during a thunderstorm. The planet's small mass also makes it an ideal target for future atmospheric studies. More massive planets have dense atmospheres that can obscure their deeper layers from observation. However, this world's thinner atmosphere will allow the Webb telescope to study its composition in greater detail, potentially revealing atmospheric chemistry details that would be impossible to detect on more massive planets. Indeed, the discovery of this low-mass celestial body confirms that the Webb telescope is capable of finding and studying in detail planets comparable to those existing in our own star system. This opens new horizons in the search and analysis of Earth-like planets, bringing us closer to detecting worlds not just potentially habitable, but actually inhabited by living organisms. The lightest planet ever photographed marks the beginning of a new era in the search for life beyond our planet. The discoveries made by the James Webb Space Telescope are merely harbingers of a golden age in the exploration of extraterrestrial life. Planned observatories and technological innovations in the next 2 decades will radically change our capabilities to detect and study life on distant planets, eventually allowing us to discover a universe teeming with biological activity spanning the entire galaxy. The most ambitious of these prospective projects is the Habitable Worlds Observatory, a space telescope designed specifically to search for and analyze Earth-like planets orbiting Sun-like stars. This observatory will use advanced coronagraph technology to achieve contrast ratios of 10 billion to 1, enabling direct imaging of planets very similar to our Earth. The telescope will be able to detect signs of oxygen, water vapor, and other biosignatures in planetary atmospheres that may indicate the existence of life. Ground-based observatories are also pushing the boundaries of what is possible. The extremely large telescope, currently under construction in Chile, will feature a mirror more than 30 meters in diameter, almost 5 times larger than the Webb telescope's primary mirror. This enormous telescope will be able to analyze the atmospheres of nearby exoplanets with unprecedented detail, potentially detecting dozens of different molecular compounds that could indicate biological activity. However, the future of the search for life is not limited to building ever larger telescopes. Artificial intelligence and machine learning algorithms are being developed to analyze the colossal amounts of data that these observatories will generate. These systems will be capable of recognizing patterns in atmospheric chemistry that may be too subtle for human detection, potentially allowing for the identification of life forms based on entirely different biochemistry than what we observe on Earth. The next generation of life detection technologies will also focus on so-called agnostic biosignatures, chemical signals that may indicate the presence of life without requiring prior knowledge of how that life functions. Instead of searching for specific molecules, such as oxygen or methane, these methods will aim to detect patterns of chemical disequilibrium that can only be sustained by active biological processes, regardless of the specific biochemistry. Perhaps the most exciting direction is the development of technologies that will allow for real-time detection of life. Future observatories will be able to track changes in planetary atmospheres over hours or days, potentially observing the daily breathing of entire biospheres. These observations could reveal not only the presence of life, but also active biological cycles responding to planetary rotation, seasonal changes, and other environmental factors. The future will also bring the possibility of directly detecting technologically advanced civilizations. Advanced observatories will be sensitive enough to detect signs of industrial processes in planetary atmospheres, artificial lighting on the night sides of planets, and other indicators of technological activity. The search for extraterrestrial intelligence will become an integral part of exoplanet exploration, allowing for the detection of not only life, but also civilizations scattered throughout the galaxy. Within the next 2 decades, we may discover hundreds of habitable worlds, each with a unique atmospheric chemistry and evolutionary history. The universe may turn out to be not just habitable, but overflowing with life, with biological processes occurring on scales exceeding anything that has ever happened on Earth. The future of the search for life promises to answer humanity's ultimate question: are we alone in the universe? It appears the answer will be a resounding no, and we will soon learn how large our community is. The world stands on the brink of the greatest discovery in the history of civilization. Without fanfare or pomp, the moment of truth will arrive. A scientist, working in a laboratory, intently gazing at a computer monitor displaying data from the James Webb Space Telescope, will suddenly realize that humanity's cosmic solitude has ended. The evidence will be so compelling and irrefutable that there will be no doubt. A unique combination of atmospheric signatures can only be explained by the presence of life actively transforming the chemical composition of an entire planet. In that very instant, everything will change fundamentally. The discovery of signs of life on K2-18b has already brought us tantalizingly close to this epical moment. With a statistically confirmed 99.7% probability, chemical indicators of biological activity have been found 120 light-years away. The detection of dimethyl sulfide in the planet's atmosphere, the complex interactions between methane and hydrogen, the chemical imbalance that can only be sustained by active biological processes, all point to the existence of a world where life is not merely present, but thriving on a planetary scale. However, the moment of absolute certainty will come when multiple independent observations confirm what we are already almost sure of. Different telescopes will register the same biosignatures. Alternative explanations will be methodically ruled out. Statistical confidence will rise from 99.7% to 99.99%, and then to a degree of certainty that leaves no reasonable doubt. When this moment arrives, its implications will touch every aspect of human civilization. Science will undergo a revolution as we confront the reality that biology is not unique to Earth, but a fundamental characteristic of the universe. Philosophy and religion will be re-evaluated as we reconsider humanity's place in a cosmos now revealed to be inhabited by other forms of life. Technology will accelerate rapidly as we develop new methods to study and potentially communicate with life on distant planets. The psychological impact on humanity will be immense. The realization that we are not alone will end the cosmic loneliness that has haunted our species since we first gazed at the stars and wondered if anyone else was looking back. We will become part of a galactic community of living worlds, each following its own evolutionary path, but sharing the fundamental experience of existence in the universe. But this moment will also bring new responsibilities. As we discover more and more habitable worlds, ethical questions will arise about our responsibility to protect and preserve life throughout the galaxy. The discovery of extraterrestrial life will force us to develop new principles for understanding our relationship with the cosmos and our role as a species exploring space. The moment we are no longer alone will mark the beginning of a new chapter in human history. We will transition from a species wondering if life exists elsewhere to a civilization that knows life exists throughout the galaxy. The universe will transform from a vast, lifeless expanse into a cosmic ecosystem teeming with biological activity and evolutionary experiments. Looking back, we will realize that the detection of biosignatures on K2-18b by the James Webb Space Telescope was humanity's first step from cosmic isolation to galactic citizenship. The chemical signs discovered in the atmosphere of a world 120 light-years away will be remembered as the evidence that ended our solitude and began our understanding of our place in a living universe. The moment we are no longer alone is almost here, and everything is about to change. The James Webb Space Telescope peered 120 light-years into space and discovered something that will change all our perceptions of our place in the universe. In the atmosphere of planet K2-18b, shrouded in hydrogen clouds and heated to 120 degrees Fahrenheit, life is stirring. The evidence is undeniable. Dimethyl sulfide, a molecule produced only by living organisms, is present in concentrations detectable across interstellar space. The statistical confidence is 99.7%, as precise as any other scientific fact. The atmospheric chemistry tells a story of biological processes occurring on a planetary scale, transforming the atmosphere of an entire world with the collective breath of countless organisms. The discovery of water vapor and carbon dioxide in the atmosphere of exoplanet K2-18b, located 120 light-years from Earth, has been a true sensation. This giant world, 8.6 times more massive than our planet, orbits a red dwarf in the habitable zone, where liquid water and thus various forms of life could theoretically exist. However, K2-18b is not an exception. The James Webb Space Telescope has revealed a universe where potentially habitable worlds are ubiquitous, offering unique conditions for the emergence and development of organisms. From protoplanetary disks surrounding young stars where planets are just forming, to ancient red dwarfs that will shine for trillions of years, the entire galaxy appears to be teeming with places where life can not only survive but thrive. These discoveries have far-reaching implications that extend beyond astronomy. We are witnessing the end of humanity's cosmic solitude and the realization of ourselves as part of a galactic community. The universe is no longer an empty space with rare pockets of life. It is now a vast ecosystem where biological processes unfold on scales exceeding all known events in Earth's history. The technologies that enabled these discoveries represent only the first step. In the future, new observatories will be able to detect atmospheric signatures of hundreds of habitable worlds, each with its unique biochemistry and evolutionary history. We may discover forms of life based on entirely different chemistry than what we observe on Earth, allowing us to expand our understanding of what life can be and how it originates. The moment we definitively confirm that we are not alone in the universe will be a turning point in the history of human civilization. Children born after this will grow up knowing that life exists everywhere in the galaxy, and that we are part of a cosmic community spanning entire star systems. The philosophical and spiritual implications of this discovery will affect all aspects of human culture. But perhaps most importantly, these discoveries remind us that life in the universe is not just possible, it appears to be inevitable. Wherever suitable conditions arise, life emerges and transforms the surrounding world. The chemical signs detected by the James Webb Space Telescope are not merely proof of life on distant planets, but evidence that the universe itself is fundamentally alive. The James Webb Space Telescope has given us our first glimpse into our true cosmic neighborhood, showing that we live in a galaxy where life is not an exception, but rather the rule. We are no longer alone, and never have been. The universe has been waiting for us to develop the technology to see what has always been there. The cosmos, teeming with life, breathes in the rhythm of countless biospheres, full of possibilities that we are only beginning to comprehend. The universe is alive, and we are part of its story. Friends, thank you for your attention.